This is a tutorial on debugging blocks in Capsim using the GDB debugger, and it applies both to the Windows environment using MSys and minimum GNU Windows or MINGW, and it also applies to Capsim in Linux or Mac OS systems. So what we're going to do is actually create a new block, and then we're going to add code in it which is going to cause it to crash, and then we'll use a debugger to find out where it crashed and then fix the code, compile it and link it again and run it again. So this will show you how to use GDB in order to debug Capsim blocks. So here we have an empty directory called debug, and first thing we're going to do is create a custom block that's going to square its input and multiply it times a gain determined by a parameter. So the first thing we do is we just type source or bash under Linux $capsim. We're going to use the pre-capsim script, and this will create all the blocks and create all the directories we need, as you can see here. Now always type make following the first time you run pre-capsim. So if we look at the directory here, let's actually clear this out. You'll see that we have a blocks directory, a make file that was created, Capsim that was just created, that's executable, also kernel block live.o, which is linked into Capsim. The blocks directory is where we're going to place our blocks, and right now all it has is a dummy block, cdummy.s, and the block database and a make file for creating blocks. So the first thing we're going to do is let's go ahead and test Capsim as we just created it, and we'll shrink this window. Let's create a new blank topology, and first thing we're going to do is just place a sine wave and a plot block. Let's go ahead and connect these up, run the simulation, and we just generated a sine wave. Let's go ahead and save this topology. Now make sure when you save the topology you're saving it in the tutorials directory. Let's just call this test debug. Okay, so we know the Capsim is operational, and the next step is to actually create a new block. So let's change directives into the blocks directory. So here we're typing the command wish $capsim tools blockgen.tickle, which will bring up our block generation utility. We get the two windows blockgen and the parameters. First thing you want to do is first of all set the block type to a processor type, the buffer type to float. So we'll call it debug block, and the parameters, we're just going to add a parameter that's going to specify the gain. So we have the gain for square operation. That'll be the prompt. Default value is 1.0, and the name of the parameter that's going to be used in the C code is gain square. Type is floating point. You say add parameter, and it's over here. Of course we can delete this if we needed to, make a change and add it again. We can save and restore it for later use. For now we'll just go ahead and generate the block. So the block is a type processor, the buffer is a float, and the block name is debug block. Okay, so let's get rid of this. Now let's do a clear operation here and see what happened. We list the directory, we see that we have a new block called debug block.s. So I just typed clear and cleared the screen. What we're going to do is edit this block and add some code to make it square its input. So let's go ahead and bring up the editor. So here I'm using the JEdit text editor, and I've opened up the debug block. Here's the block name between the XML tags. Let's go down. Here we have the parameters. The parameter that we defined, which was the gain for the square operation, we called it gain square. That's the variable that's going to be used in the C code. It's type float, and its default value is equal to 1.0. Now, when we generate this block, a default parameter is also set up in order for users to be able to generate their own parameters. We'll just get rid of this. We don't need it. There's also a dummy state setup, so you can see how a state is set up in case you need to add your own state variables. Now here we have the input buffer, and its type is float, and its name is X. We have an output buffer, type float, and name is Y. Basically, we're going to input an X samples, and we're going to output samples into the Y buffer. Input and output, and process a sample in between. Here we're showing the main code. So this while loop basically iterates on the input buffer, and as long as we got input samples, it'll continue to consume and process those samples, and once it's done, it'll return back to the kernel. It in 0 basically increments the input buffer and sets the pointer to point to the most recent sample, and we're just taking that sample x0 and place it into the variable sample here. And on the output, we're going to prepare the output buffer by incrementing it, iterate out 0, and that makes it ready for accepting a sample, and then we'll just place sample on the output buffer Y. That's simple. Input the sample, output the sample. Now what we're going to do here is we're going to multiply sample by gain square, which was the parameter, and as we mentioned, we're going to square the sample. So we're squaring the input and outputting it. All we have to do now is save this, and we're in the blocks directory. If we do a list, we see the debug block. We just changed it. We cd back to our top level, which was to debug, and all you need to do is type make. Now notice that we're actually compiling debug block.c over here using GCC, and we don't have any errors, just typical warnings. Now because this block was just added, we have to type make again. So if you add new blocks, you type make twice, but if you just update blocks, you only type it once. Let's go ahead and run Capsim, and let's go ahead and open up the topology we had before, which was test debug, which had a sine wave connected to the plot routine here. Let's go ahead and run that. So it just basically plots a sine wave. And what we're going to do is get rid of this connection, and we're going to add our new block. It should be in this list here. Remember, it was called debug block, so let's go down to the D's. And here it is, debug block. So we'll place it over here. Let's move it around. Now we'll connect the sine wave to the debug block. One thing I want to do is add a probe here, which is a plot probe, which will plot the sine wave before squaring it, and we're actually plotting it after squaring also. Let's go ahead and save our work. Let's take a look at the parameters here. Notice that we have our parameter, the same prompt we had, gain for square operation. Type was float, and the default value was equal to 1, just as in the code. This is exactly the code we had over here. So if you look at the parameter block here, here's the definition. This is a definition, the type, and the name of the variable. If we go back here, exactly what we have over here. So now let's go ahead and run the simulation. Now we get two plots. This is the original sine wave, and this is the square of the sine wave, and we can see that, first of all, it's a cosine of the second harmonic. So we go from 0 to 1, and we double the frequency. That's due to the squaring operation. So our block is working per our requirements, and everything is fine and dandy. Now the idea here is to actually add some code that will cause this block to crash. Make sure we save our changes, get rid of all the plots, actually shut down Capsim, and let's go back to our code here for the block. And what I'm going to do is add a new pointer called crash into the declarations, And then what I want to do is cause this block to crash. So in the code, in order to cause this to crash, we're going to actually set crash equals to 2. Now remember, crash was a pointer, so we're setting its value equal to 2. This should cause a segmentation fault. Let's go ahead and save this, and we'll type make. Again, we're compiling debug.c. There are no errors, just your typical warnings. Let's run Capsim and see if we can crash this thing. So let's go open up our debug topology. Here it is. Let's go ahead and run Capsim. Sure enough, we crashed, and we got a segmentation fault, core dump. All hell is broken loose. So what we need to do is run Capsim with the debugger to find out exactly where that crash occurred. So now we use GDB, and this will work on, as you can see, Windows or under Linux and Mac OS, the same. So we'll type GDB Capsim in order to debug Capsim. Then we'll type run to run the simulation. Now what I'm going to do is place the window here so we can see what's going on in the debugger. Let's open the topology, debug test, and now we'll run the simulation and we get a crash. So the debugger is telling us that debug block.c has crashed at line 194. Let's go ahead and use the editor here and open up debug C, and let's go ahead and look at first of all, let's show the line numbers here. Let's go to line 194, and here it is. So it's telling us we crashed right over here, and that's exactly where we expected to crash. So we can fix this by commenting this out and running the simulation again. Now before we do that, notice that the debug points to the C code as it should, not the XML code. So you have to, when you get a message from the debugger, you have to actually look at the C code, not the XML code, and figure out what the problem is in the C code, and then edit the XML code in order to correct that problem, as we'll show in a second. So you have to maintain the XML code when you make fixes based on errors that you see in the debugger, but the debugger will point to the C code, but it's very clear as to where in the XML code you need to make the change, because there's a nice correspondence because of the modular nature of the XML code. There's a couple of other things that I want to show about the debugger before we move on, and that is the debugger, you can actually use the display command, and let's take a look at what the sample value was. It was equal to 1. And if you go into the C code, you'll notice that the parameters within Capsim and the states are defined using define statements. So if you look at the parameter defines, the actual parameter gain square is a definition because it has to point to the parameter block, so it's saying it's the first parameter, which is parameter 0, and its value is of type floating point. So if you want to actually get to the value of gain squared, you can't say just display gain squared. You have to actually say display this variable. So what you do is you park this over here, and let's just do that. So let's go ahead and type that. So if I want to know what the value of the parameter was, and since you don't change the values of parameter, this is not really an issue, but this is just to highlight how things work. So I'll say display param, and this also highlight the fact that the debugger allows you to go deep into data structures, and as you can see, its value is equal to 1. Next time we're going to change that, and we'll show you how you can get it. Also, if you add a state, we have a state variable here. It's also using a data structure, state underscore p, and within that data structure, the actual state variable, this is the name of the state variable, is preceded by 2 underscores. So that's how you can get access to the state variables within the debugger. You probably need to check the states in order to do some debugging, but typically all the variables that you need, you just say display. That's all you need to do. For example, if we say display crash, then it'll show its value. Of course, this is pointing to some location in memory. It's a pointer. So essentially, we've found out where we crash in the C code, which was right over here. I'm going to comment that out in the C code, and that doesn't help me one iota because you need to change the XML code. So here's the XML code, and let's go ahead and comment this out. We'll save it. We'll exit the debugger, and we'll type make to incorporate the new change. We'll run Capsim, open up the topology, and this time we'll run, hopefully we won't crash, and sure enough we don't crash, and we get our two sine waves. What I'm going to do is exit out of here and just show you, basically let's go ahead and make this guy crash. Is I'm going to change the value of that parameter, and then I'll show you how to access the value of that parameter within the debugger. Also, let's go ahead and take a look at this state variable that we have over here. Here we got this thing called state variable, and I'm going to change its name to test state. I'm going to set its default value to 888, and what I want to do is access this through the debugger. So let's go ahead and save this. So now we've added code to crash again. Let's go ahead and type make in order to update Capsim using the new block, and we got to make sure we use a debugger. Run. Let's open up the topology, and we should crash, which we do. Okay, so again at line 194. Now there's a couple of things I want to demonstrate over here. First of all, let's go back to the editor, and let's go ahead and take a look at the C code. Okay, so now I've opened up the C code. Remember that this is where we crashed, and if we take a look at the line numbers, let's go to 194 just to double check. So just as the debugger said, line 194, that's where we crashed. Now, let me highlight how to get access to state variables in the debugger. So here we have a new state variable called test state, and as you can see, test state is actually a define. So if I wanted to see what the value of test state was, I need to examine this variable within the debugger. So let's go ahead and use the display facility within the GDB. So we just say display state, and of course if we can do cut and pasting, that'd be nice. So we'll just do that, and there it is. That's the value which we had set for by the default, which is 888. Let's go ahead and look at the XML code. If you recall, in the XML code, when we defined the state, we defined the state called test state, and we set its value to 888. Actually, since it's a integer, we only need to set it to 888. So here it is, exactly what we had. So this is how you can get access to state. Just go look at the C code, find out what the definition of it was, and then refer to the definition. Same with the parameters. Let's go ahead and quit this. Now this time I'm going to run the debugger, but before running I'm going to change the parameter. So over here, let's go ahead and change this parameter from 1, just for the heck of it, to 1, 1, 1, 2, 2, 2, and 3, 3. So I've changed the parameter, and then I'm going to run. We crash. Let's go ahead and take a look at the C code. If you look at the parameter defined, in order to see what the parameter for gain square is, I need to examine this data structure value, the element within the parameter data structure array. So I just say display. This is kind of awkward, but you never change parameters in the C code. You change them through the dialog, so you seldom have to do this, but just in case, just examine it, and here it is. That's the value of the parameter, which was 11112233 as we had set within the topology. One nice feature of GDB is the command where, and when you type where, you get this stack of where the crash occurred. And this is very interesting because sometimes you have a block which is calling a routine within a subroutine, so you can find out which block called that subroutine, and you can go up and down in terms of looking at the variables within the subroutine, and then you can type up to then look at the code and examine variables within the code that actually called that subroutine, etc. So GDB is extremely powerful. Debugger, which we use in Capsim in order to debug blocks. Now, sometimes when you crash in Capsim, it may turn out that the fault is not the block where the crash occurs, because a previous block might have, for example, overran some memory that was allocated, say an array, etc. So sometimes you need to go look at, especially blocks that you generate, you create, you got to make sure that when you allocate memory, and especially for arrays, etc., you don't overrun the indexes or the bounds of that array, and that could actually cause blocks down the simulation chain to actually crash. That doesn't happen too often, but double check your code. So we've demonstrated that debugging Capsim is very straightforward. We use the powerful GDB debugger, and there are books on GDB and how to use it, and it is very easy to find out where the crash occurred and examine the variables and figure out what is going on.